First, we built the quantum field theory for scalar fields, which correspond to spin zero, so objects which transforms as scalar under Lorentz transformation. We built Lagrangian, arguing that the action, which is a space-time integral of the Lagrangian density, should be a Lorentz scalar as well. Then we used the many-path formulation of quantum physics to build an amplitude of probability for the field to go from vacuum to vacuum over an infinite time. We recovered the classical limit using the variational stationary action principle. We then return to the quantum case in the case of free fields, so fields which are up to a quadratic term in the Lagrangian, so higher order terms correspond to interaction within the field. So by switching off these terms, we were able to write our amplitude as a Gaussian path integral, and then to solve it, we then got the effective action from which we determined the free propagator for disturbance of the field which propagates without interaction. And from this, we were able to recover that the disturbance of the field which propagates on mass shell corresponds to particle. And also we were able to investigate the interaction between sources. The process we use as a guideline to build our quantum field theory is the annihilation of electron and positron into muon and antimuon. In this process, there is no particle with a spin zero. The electron and the positron, as well as the muon and the antimuon, have spin 1/2, and the mediator for this interaction, the photon, has spin 1. So we decided to generalize our quantum field theory to vector fields which allow us to describe spin 1 particles. In order to build the Lagrangian for vector fields, we started with the classical field equation of motion, and from that we argued that they should obey Klein-Gordon equation because the particles should have E squared equal P squared plus M squared, which doesn't depend on the spin. So we got our Lagrangian. We built our path integral, which we solved for free fields, and we obtained the propagator for free vector fields. And then we got the Coulomb interaction between charges acting as sources on the field. By taking the limit where the mass goes to zero, we can describe electromagnetism, and therefore the mediator for the interaction, which is responsible for the annihilation of electron and positron into muon and antimuon. But that's obviously only part of this diagram. We still have to describe spin 1/2 particle. So that's what we will do now. We will introduce spinor fields. We will build our Lagrangian by requiring that the action is scalar and that the field obeys, in the classical limit, the Klein-Gordon equation. Quantizing the theory for spinor fields is not straightforward and could take us very far. However, what we are interested in essentially is a propagator for fermions. So we will actually take a shortcut to get the propagator without having to introduce too much formalism. We won't go to the interaction between sources with the spin 1/2 field. The reason for that is that usually particles do not interact through the exchange of spin 1/2 virtual particles. So spin 1/2 field is usually not the mediator of interactions. And I'll let you think why. We also see in this diagram that we have both particles, the electron and the muon, and antiparticles, the positron and the antimuon. So we will see why we must have such antiparticles, why quantum field theory dictates that we have antiparticles, and for that we will use the Noether theorem. We see that we also have to account for the possibility for the electron and the positron to disappear and then become a photon at some point of space-time which is called a vertex. And such vertices appear when we have interaction within the field, so for instance with the phi3, phi4 terms, etc., or terms in the Lagrangian which will mix up the different fields with different spins. And one difficulty is that with such interactions, the theory is not solvable anymore. We need to use approximations, for instance perturbation theory, and that's when Feynman diagrams like this one become useful, or other type of approximations like effective field theory, etc. At this stage, we will be able to describe basic particle physics processes like this one. We will also be able to investigate some important ingredients of the standard model, like the Higgs mechanism, and eventually we will also be able to apply the tools and concepts of quantum field theory to condensed matter systems, nuclear physics systems, etc.